Hello, everyone. So we are ready to start the third session. My name is Cindy Rubio Gonzalez from the University of California, Davis, and I will be chairing this session. So our next keynote speaker is Manu Sridharan. He's a professor of computer science and engineering at the University of California, Riverside. And today he will talk about lightweight resource leak verification and inference.
Thanks a lot, Cindy. Can everyone hear me? Yep. Great. So I'm very happy to be here. Thank you for the invitation. This is work that was done with several collaborators. I want to specifically call out those who were students or postdocs when they did this work. So Narges Shadab, my recently graduated PhD student who's now at Oracle. Martin Kellogg did some of this work when he was still a PhD student. He's now a faculty. And Preetham Garat, when she was a postdoc at Microsoft Research, did a lot of the work here. So I wanted to give proper credit. The collaborators were absolutely essential here. Okay, so resource leaks. What is a resource leak? In a language like Java, of course, you have the garbage collector to help you manage memory. But even so, there are particular types of resources where you should be explicitly doing a function call to release that resource. You can't just rely on the garbage collector to manage it. So here's an example. We have a socket, and you're supposed to close it. And if you forget to call close, that leads to a resource leak. There's some underlying operating system resource that doesn't get reclaimed in a timely fashion. And besides sockets, other resources that you have to manage explicitly, including things like file handles, database connections, there are potentially many other examples. So any type where you explicitly need to call some finalizer function before it goes out of scope is potentially subject to resource leaks. And resource leaks cause a lot of real-world problems. Resource starvation, they can cause slowdowns or system crashes, even denial of service attacks, right? If someone knows a way to like force your service to just allocate more and more resources without releasing them. And these are pretty nasty to try to debug with testing, right? Often these won't manifest in an obvious way with your unit tests or even your integration tests. They'll manifest when you've been running your service for a week and all of a sudden it's getting really, really slow. And you're not sure why. And so, I don't know, you end up having to reboot it or something. And then a week again, it happens again, right? We'd hope to do better, right? So for many, many years, people have worked on automatic techniques to try to statically detect or prevent resource leaks. So I can give a very rough categorization of existing approaches. We can kind of put them into three categories. The first is heuristic tools. These are often built into your IDE. Eclipse has a resource leak detector. IntelliJ has a resource detector. And these tools run very quickly. They can give you reports without taking a long time. But in our experience, they're both unsound. They miss real issues. And they're also kind of imprecise. They report a lot of false positives. So hopefully we can improve on that. Another approach, which has been pursued in multiple different systems, is whole program analysis. For example, there's a very nice paper from ICSI 2010 by Meena Torlak, Satish Chandra, effective interprocedural resource leak detection. And people have built on this. Grapple is a recent system that does this kind of whole program analysis. Tends to be more sound, catches more issues, more precise than the heuristic tools, but it can take a long time to analyze a big program. We'll show for Grapple, it's on the order of hours for larger programs. So that's not great if you're trying to, fit this into your developer workflow. And finally, and more recently, there are techniques like ownership types, right, as in the Rust programming language, which basically, if you're using it in the intended way, they get rid of resource leaks, right? You get various guarantees that when an owned pointer goes out of scope, it's going to be finalized and closed properly. So this is, sound and quite precise, but we're interested in tools that'll apply to Java and the type of aliasing restrictions that are required to fit your code within the Rust type system. It's kind of very difficult to retrofit that onto existing Java code. So what would we like here? Kind of an ideal checker for these kinds of resource leaks. We'd like it to be sound, or at least, soundy, catch as many of the real bugs as we can. Of course, we want it to be precise. We'd like it to be really fast, right? With modern development workflows, it would be great if you could run this as part of your continuous integration and report issues before they even land on your main branch. And we want it to be applicable to existing programs written in Java or C#, those style of languages. And just looking at this list, you might be wondering, hey, it's pretty hard to accomplish all of these things with pure static analysis. And I'm not going to claim that we've done all of these things simultaneously perfectly, but I think what we've done is found a new point in the design space that I think is valuable in many scenarios and is worth exploring and trying out further. So what did we do that was different? Like kind of what are our kind of new ideas? So one key insight is that we figured out that we're able to do very targeted reasoning about aliases, specifically if you're trying to solve the problem of preventing resource leaks. So we've defined this class of type state properties called accumulation properties. And the interesting thing about them is that you can do sound type state checking without doing a whole program alias analysis. Now, it doesn't mean it's going to be precise, but at least you can have a core sound technique, and then you can try to improve its precision by layering on targeted reasoning about pointer aliasing. Okay? So that's kind of at the core of our approach. If you can kind of track the right set of must aliases, you'll be in good shape. But that kind of raises the question, well, how do we know which of these aliases we actually need to track? And here, I've been doing a lot of work over the last few years on pluggable type systems, right? Where you add some additional annotations to your code and it enables checking of correctness properties kind of within the compiler, almost like a type checker. And that's the approach we use here, where we've defined sets of code annotations that expose the really important aliasing and ownership properties to get more precision in this resource leak checker and capture the patterns that are used in practice. So this is great because now when we're doing this as a type checker, we can do modular checking, right? We can type check one file at a time. Incremental analysis basically comes for free. It runs really fast compared to whole program static analysis techniques. And now there's always the question of, well, what about existing code, right? I've got a big code base. Who's going to go through and write all these annotations? So after we developed this checker, we also developed an inference technique. I call it optimistic inference, and I'll tell you why later, that we showed is pretty effective at easing this initial annotation burden if you have a big code base and you haven't been running our checker yet. You can run the inference. That should give you a good initial set of annotations, and you can kind of go from there. So I'm going to tell you the technical details of some of the technical details, anyway, of what we've done. But this is the work I'd like to describe to you today, and it's available for people to use. So it's available as part of the checker framework. It's called the resource leak checker, and there's also an implementation RLC Sharp for C# code built on the CodeQL platform. So I'm excited about this work. And first, I'm going to tell you about the core pluggable type system that we defined that we use to verify the absence of resource leaks. And then finally, I'm going to get into some detail. We see how much time I have left on this inference technique to automatically add the necessary annotations to your code. And I forgot to say at the beginning, but I'll say it now. I'm really happy to take questions at any point during the talk. No need to save them for the end. Just raise your hand. Let's try to keep this interactive. OK, so let me first talk about the lightweight resource detection based on pluggable types. And taking a step back here, the broader context of verifying these types of properties falls in the field of type state checking. And in type state checking, you have objects that transition between different states as you perform operations on them, but certain operations might be illegal in certain states. So here is automaton, a type state automaton, describing what are the legal and illegal transitions for a file object. And you can see that whenever you transition to error, that's an illegal transition. So if you call open on a file and then try to open it again, you end up in the error state, right? So that's one of the things that you shouldn't do with these file objects. So the goal of type state checking or verification is to check that in your program, none of your objects can ever transition to this error state. Okay? So this is, again, a problem that's been studied for decades. And the key challenge here in doing type state verification at scale is dealing with pointer aliasing, right? Because the problem is that your object state might transition through any alias of that object. Doesn't always need to be the same variable. Here's an example where we have 2 calls to open. So this is a problem, but it's through 2 different aliases. So you have to do alias analysis to keep track of this stuff. And the previous approaches, I gave you this breakdown before. You can also kind of break them down by how they handle this problem of pointer aliasing. So the heuristic bug finding tools, for the most part, just ignore aliasing. And this is what leads to them being both unsound and imprecise. Then we have the type-based alias control, right? So this was the ownership types in Rust, basically give you strong restrictions on how you create and use aliases. That helps a lot in verifying these properties, but it's hard to migrate existing Java code to use that kind of discipline. And finally, there's whole program alias analysis, right? Just try to track all the aliases, but this is hard to scale and hard to turn into an incremental analysis that's suitable for CI. So we looked at this problem, and we observed that there were certain types of properties where you can actually do verification without doing a whole program alias analysis. Now, doesn't mean it's going to be precise, but it'll be sound, okay? So that's kind of the basis of this work, this idea of an accumulation property. That's what enables this kind of modular type-based checking. I'm not going to get into all the formal definitions of what is an accumulation property. You can see our eCoop 2022 paper for all the details, but the intuition is that you have type state systems where certain operations enable some other operation of interest, right? They make them legal, and once that operation becomes legal, it can't be disabled, okay? There's nothing else that's going to make it illegal. So again, I'm kind of hand-waving, but you can ignore the aliases because once you see that this, how do I put this, right? If you ignore the aliases, then you're going to get false positives, right? Maybe some other alias made this operation legal and you missed it, so you report a false positive, but you don't get false negatives, right? All you can miss is kind of things that made the operation legal, but you never miss an operation that makes it illegal again, because that's not possible. So how do resource leaks fit into this world of accumulation? Well, here's our assumption about a Java-like resource. We assume that, you know, it's in an open state, you call close, and then it gets closed, and we're not trying to detect like kind of the equivalent of a double free error, right? We assume closing it multiple times is fine. So what is the operation that kind of becomes legal? If you squint, it's basically this operation of going out of scope, right? Once you close a resource object, then it's allowed to go out of scope without leaking. But if you allow it to go out of scope and you lose all the pointers to it before you've closed it, then that's a bug, right? So once you've closed it, there's no way you can kind of unclose it and cause a leak again. So it's an accumulation property, and that means that if you want to build a sound resource leak detector, again, ignoring precision, you don't really need a whole program alias analysis. And it's very simple. I'll just walk through a simple example, but the core leak detection approach is to just look at different references, different variables, compute what methods are required to be called on those variables, you know, methods like close, and then you compute what methods are actually called, and then you look at the places where the object might go out of scope and see if there's a mismatch, right? If there's some required method that hasn't been called yet. So here's a simple example with a socket. So in terms of what's required, we call that an obligation. So here, with this new socket object, there's an obligation that you need to close it, right? You need to call close on S. And of course, we can very easily do a static analysis to keep track of what methods have actually been called on S. So at this program point, nothing has been called yet. And then after this program point, close has been called. And now with this information, we can look for errors. So like right here, we're overwriting S, right? So that's potentially making the previous socket object go out of scope and close hasn't been called yet. So that's an error. Whereas down here, after this call, we're good to go because we've closed the reference. Okay? So this is very simple. It's actually sound, but you'll see that it's way too simple, right? So if I change the code like this and close s via this variable t, the simple technique that I just defined to you will now report an error, even though this code is kind of obviously fine. So it's not precise. So this is where we need to do our targeted reasoning about aliasing to regain enough precision to make this useful. And we have kind of a suite of techniques that we use to regain this precision. This local must alias analysis is very straightforward. It's just a must alias analysis within a single procedure, nothing too interesting about it. So here in this talk, I'm going to focus on these two techniques, the lightweight ownership and this idea of resource aliasing. So first, let's look at the lightweight ownership. So in this example, I have a method close socket, which takes in a socket and then it closes it. Okay? And here I have a call to close socket passing in a variable. Now, with the analysis that I defined before, it has no knowledge of what's going on inside this close socket function. I have to say that basic analysis was intra-procedural. So we're trying to avoid doing inter-procedural analysis wherever possible to stay within kind of the type checking modular approach. So it doesn't know what's going on. It's going to assume that after this call, I still need to call close on my sock. So what we do here is we add an annotation. We call it owning. And what this tells the analysis is that this method is promising to take care of the call obligation on its parameter. It's promising to close it. And what our checker does is kind of transfers this obligation over here, right? So at the caller, it says, okay, I'm going to assume that close was called. But now inside this method, it's going to check and make sure that close is always called on the parameter. Okay, so this is sound because it's just a hint for the checker, right? It doesn't remove any obligations. It's just telling the checker a hint as to which reference is going to be responsible for disposing of this resource. That's how you're going to call close. And the key difference between this kind of lightweight ownership and what you see in a language like Rust is that this doesn't in any way restrict the privileges of other aliases, right? So you can go ahead and have whatever other aliases that aren't annotated owning. You can do type state transitions with them. It doesn't matter. This is just a hint to our checker specifically for detecting resource leaks. This is why we call it a lightweight ownership transfer. And it's much more in line with the sort of aliasing patterns in Java, right? People are not careful about what aliases they create to objects. So just having this lightweight technique that's good enough for finding leaks is really important. And we also support writing owning annotations on fields. And I'll show a more complete example with that in a couple of slides. So that's one of our techniques. Again, we're kind of telling the tool which alias is important for trying to figure out whether a resource gets closed. Another key technique we called resource aliasing. So you see examples like this a lot in Java code, right? I have a socket, and then I get its input stream and wrap that in an input stream reader, and I've got a variable now pointing to that reader. And the question is, which of these should be closed, right? You've got two references now to two different resource types. And what happens very often in Java is that you have these wrapper types where you can close either one of these, and that's sufficient to release the underlying resource, right? Another example is like a buffered input stream, right? You can close the buffered input stream, which is wrapping some other input stream, and that will kind of go into the wrapped type and make sure that its resources are cleaned up. So this is the pattern that we're trying to capture with this notion of resource aliasing, right? So these are not must aliases, right? Obviously, they're different objects, but from the point of view of cleaning up resources, we can treat them as if they're must aliases, right? Which means that if you call close on either one of them, that's going to satisfy your obligation, right? So we treat them as must aliases for the purpose of checking for resource leaks. And other works have done this in the past, but the way they did it was kind of baking into the tool a list of like all the wrapper types in the standard library. You know, buffered input stream, filter input stream. They list them all out, and then they bake in reasoning for those types into their analysis tools. In contrast, we have a mechanism via annotations. It's a resource alias annotation to create your own wrapper types, right? And you can annotate them with these resource alias annotations, and we can actually verify that it is a proper wrapper type, that it's properly disposing of the nested resource. And so this is much more flexible. And then we can use this annotation in our models of the standard library to capture the cases that are in the library. So it's kind of a unified mechanism that you can use in your own code as well, which comes up a lot in real-world code. People write these wrapper types all the time, so it's nice to have this mechanism. And let me show a more example, though again, I welcome questions at any time, but maybe we'll have questions. Here's a more detailed example. I hope the font size is readable, but basically I have this class, MySQLCon, which is wrapping one of these connection objects, right? So let's assume a connection object is something that you need to close, right? It's like a database connection. So here, we're wrapping it, and we write these resource alias annotations on the constructor that kind of tells clients that, you know, if you create a wrapper around a connection, you can kind of close either of them, right? That's what happens here. This code can be verified. In one case of the if, we close the connection directly. In the other case, we close the wrapper, and this passes our checker just fine because we know that they're essentially must aliases for the purpose of closing resources. So, but we need to check that this type is doing the right thing. So the way we do that is that we annotate this field as owning, right? So this is the reference that's going to be responsible for closing this connection. And the way it's going to happen is that this MySQLCon type needs to define a finalizer method that takes care of closing that, right? In this case, it's this dispose method, right? So dispose is the method which, via some other method, we have an annotation says this is always going to call close on the con field, right? And we verify that this annotation is correct as well. And then finally, we have a top-level annotation that tells the users of this class, if you're creating a MySQLCon object, you have an obligation to call its dispose method, right? Because that's the thing that's going to get rid of the resources that are managed by this type. Yeah, question. I think, do we have a mic?
So the resource alias annotation is the second one. Just signifies that this is the alias for this object. Is that correct?
Exactly. Like you might have multiple parameters in your constructor, and so you need to say which one is the resource alias with the new object.
Mm-hmm.
Yep.
Any other questions?
Suppose I use a library. How do I add annotations to the source code of the library because I don't own it? Can it be done externally via some models, or what do I do?
Yes, so we've built this all on top of the checker framework for Java, and it has a mechanism for essentially writing what are called stub files, where you kind of copy the signatures of methods from the library, but then you can add your own annotations, and when we're checking, we kind of use those annotations from your stub. Now, that is, we don't verify those annotations. Those are trusted. So if you actually wanted to check that those were correct, you would have to then go annotate the library source code and run the checker on that library. But there is a way, if you don't own the library, if you want to trust some annotations that you wrote, to kind of plug them into our tool. And that's, in fact, how we handle the Java standard library, is with these kinds of stubs. Okay, so it's important that we don't just trust these annotations. We do actually try to check that they're, all these invariants are being respected by the type. So let me just give you a hint. Maybe I can flip back and forth of how we verify. What are our rules for verifying these annotations? So if I have a final owning field of type T inside class C, then, okay, we look and see. T is annotated must call M, right? So M is the method that always needs to be invoked on these objects, and then the enclosing class C is annotated must call n, right? Then we want to check that this n method is always going to call m on the field, right? So there we just check for the annotation that that n method is always going to call it. So here, this is the owning field. The method that always needs to be called is close. So we need to check that this dispose method is always going to invoke close on the field. And so that rule is satisfied in this case. And then what about resource alias annotations? We have a bunch of cases for that. So here for a constructor, we check, okay, the class should have exactly one owning field, right? Because if it has multiple owning fields, you can't be a resource alias for all of those things, right? You kind of have to pick one. Otherwise, it's not going to be equivalent, right? This class is managing multiple resources, and yeah, it doesn't work. So there's exactly one owning field. The constructor should always write its parameter into that field. Okay? So we have that satisfied here. There's exactly one owning field, and this method is always taking the thing and writing it in here. So that's sufficient along with our separate verification that that owning annotation on the field is correct. Yeah, another question.
So do you do verification on the owning annotation itself? Like, because in the Rust, the ownership requires a quite complicated borrow check stuffs. It's not only related with the function that you annotate, it's also related with the core side of the function. Like if you pass ownership to the function, then you make sure you not access the resource again. So do you do check on that also?
Yeah, great question. So I talked a little bit before about how this is a lightweight notion of ownership, right? So ownership is just kind of a hint to our checker about which reference is going to be responsible for kind of closing the resource, right? Because we're only trying to check resource leaks. So in order to check resource leaks, we actually don't need to do all those other checks that Rust does. Rust is much more restrictive about exclusivity of an owning pointer and not mutating through non-owning pointers and that kind of thing. So we don't need to do that for resource leaks. So now what's the downside? Rust can actually verify the absence of issues like double free or use after free, right? You'll never have those issues in Rust. We cannot check that. So it's possible after running our checker that you'll always close a resource, but then you might try to use it afterward. And our checker is unable to check that property. Okay. So we're going solely after resource leaks, and that's what lets us do this lighter weight checking around ownership.
Okay, I see. Thank you.
Yep. Okay. So no other questions. So let me show you some results from our evaluation. So we looked at some pretty serious programs with some hairy code in them, like Zookeeper, component from Hadoop, HBase. So it was a significant amount of code. And so we found 49 real resource leaks. We reported several of these upstream and got them fixed. The precision is not that great, you know, compared to like a typical bug finding tool. And part of the reason is that we're trying to be sound here. I mean, I can't guarantee our implementation is bug-free, but we're really going after trying to catch all the leaks, and so that does lead to some false positives. Common causes that we saw were cases where you needed path sensitivity to prove that a leak wasn't happening. We don't have path-sensitive reasoning in our tool, at least not yet. Another big issue is like collections of resources. Like if you have a list of sockets and then you iterate through all of them, we're actually actively working on this, but we didn't yet have a way to verify that kind of code pattern. So that's another cause of false positives. So yeah, but we did find, you know, a lot of real leaks. In terms of the number of annotations, we think this is quite reasonable. It's roughly on average one annotation per 1,500 lines of code. And intuitively, it makes sense that you wouldn't need a huge number of annotations for this property, because you only need to annotate code that's related to resource management, like opening and closing resources and passing them around. But if you have other libraries that never touch files or sockets or any of that, you don't need to annotate them at all. So it's not like a pervasive property that it's going to impact every class in your program. So we wanted to do some comparative evaluation. of our checker, that's the RLC, resource leak checker. We compared it to Eclipse's heuristic bug finder, and we ran it in its high confidence mode, so only admit high confidence issues. And we also compared to Grapple, which was a recent kind of whole program type state checker based on like efficient graph reachability techniques. And here's kind of a summary of our results. So first, in terms of recall, and this is under the assumption that we don't have bugs in our implementation, we still found way more real resource leaks than either of these tools did. Like they just give up on a lot of real resource leaks. I think because it's hard to track all the aliasing involved and be confident in the reports. In terms of precision, Grapple did better than us. Surprisingly, the Eclipse heuristic bug finder, even in high confidence mode, had roughly the same precision as our tool. And here again, I think it's because you need to track aliasing both for soundness and for precision, right? Like if you don't know that there's a wrapper type that it's legal to close the resource through that wrapper type, then you're going to report a false positive. Like that's an alias that you need to track for precision. So this I was kind of surprised by. I thought they would be much more precise, but even in their high confidence mode, Eclipse's false positive rate is roughly the same as ours. And then in terms of running time on some of these huge programs, Grapple took over 36 hours. Eclipse is a little bit faster than us. It's hard to see on this chart. I didn't zoom in to show that, but our running time is quite reasonable, on the order of a few minutes. Yeah, question?
What happens if you decrease the confidence that you require from Eclipse? So I could imagine that the recall goes up. Is it anywhere close to your tool then? And the precision will likely go down. Is it really bad, or is it just a tiny fraction?
Yeah, good question. I think when we ran Eclipse in low confidence mode, we were just overwhelmed by the number of reports, and so we didn't have the cycles to do a very careful triage of all of them. I think thinking back, we should have at least checked the recall, so that's something maybe we should go and look and do, but the precision becomes terrible, like absolutely terrible.
Well, obviously, if you know the results from your tool and you have checked that, you can still check whether Eclipse finds at least those. And
Yes.
if it doesn't, then it's out of the question and garbage, but
Yes.
if it does, then it would be interesting what the trade-offs are.
Yeah, so I'm quite confident that this precision bar, because we know what the real issues are, and it was reporting like hundreds more issues, so this is going to go way down. How far this comes up, I'm not sure. In my subjective opinion, it's kind of getting beyond the point of, if it's, 1 out of 20 reports is a true positive, that's getting kind of hard to triage. But yeah, we should measure that and check that more carefully, at least the recall.
A question. So, and about your ground truth. So, what are you using as ground truth?
Yeah, we make the probably unsafe assumption that our tool. So we're ignoring bugs in our tool. We just look at all the reports from our tool, which is intended to be sound. So that's where we triaged all of these reports. So that's what our ground truth is. But there's a threat that like there's even more true positives, and due to bugs in our tool, we didn't find them.
Thanks.
Okay, so that pretty much covers what I wanted to say about our checking tool. Again, it's open source. It's available as part of the checker framework. You can run it on your own code. So now I wanted to return to, oh, sure.
Just one question. So we had a similar problem that in another work that we didn't know how to get a ground truth. So what we did is we looked at all the outputs from all the tools and verified them by hand, and then this would avoid normalizing our own recall to 1. So what if there was something in the Eclipse recall, like one instance that your tool did not have, or be it something you overlook conceptually, some bug in the implementation? Because with that, you're normalizing your own recall to 1, right?
Yeah, I see what you're saying. We did look at a significant number of the Eclipse reports by hand, but I don't think we exhaustively went through all of them. So for what we did, we never saw a case of like a true positive that we missed, but yeah, we could have systematically gone through every single one to kind of double check that.
Pick a random fraction of n or something like that.
Yeah. So yeah, I don't know if we were systematic about it, but we did look through a bunch, and we never saw a case where it was a true positive that was missed by our tool. Right. So we built this checker, sound, modular implementation bugs. I would argue relatively precise in that we're kind of matching the precision of Eclipse's high confidence mode, particularly given that we're also trying to be sound. And scalability is good, but there's still one problem, right? Which that we rely on these annotations. And although the absolute number of the annotations wasn't that high, it was still, moderately painful for us to go through and write these annotations on these real-world programs. Like, it took several weeks for our case studies. Now, you might say, oh, but you weren't the original programmers, right? And maybe they would have an easier time. But in reality, who knows who wrote that code, right? It was some previous maintainer. It's going to be a challenge to do this all by hand. The patterns are kind of tricky. You have to do a lot of thinking about exceptional control flow paths and stuff. So this is a hindrance to wider adoption, and this is what motivated our work on automated inference, right? Can we build a tool to help in writing these annotations? So that leads to the next part of our talk on inference of resource management specifications. Here, I think I'm going to be kind of brief. How much time do I have left? 15 minutes. Oh, okay. I'm doing well. So let me just give you an overview of this approach. So I think you can see that the kind of checking that we're doing as part of the resource leak checker is not just standard subtype checking at assignments, right? We're checking various aliasing related properties that are interrelated, right? According to resource ownership, these resource aliasing relationships, these call obligations. We couldn't just take an off-the-shelf inference tool for pluggable type systems and use it for our system. We needed to develop something custom. And I think probably the most interesting thing about our inference is that it's optimistic, right? Very often, there are bugs in the code that we're trying to do inference for. And so rather than being very strict and only inferring annotations that will be verified, we attempt to figure out what did the developer intend to do. And once in a while, we'll infer an annotation that will not be verified, that will cause an issue, in fact, to be reported, but we still think it's the right thing. And it'll cause the issue to be reported in a better place. And I'll give an example of this on the next slide. So overall, we formalize this as just a set of inference rules. If you look at the paper, it's using like a data log style syntax that we just run to a fixed point. And we actually have two different implementations of this inference. We did it for our existing Java implementation of the resource leak checker, and also we had a collaboration with a bunch of folks at Microsoft. They had actually independently looked at our paper and started working on re-implementing the same checking technique for C#. And then Nargis, my PhD student, went and did an internship with them, and they worked together on completing that checker. And also we got an implementation of inference for C# as well. So let me give you a simple example of this optimistic inference. So here's a cleanup routine that takes in a socket, and first it calls shutdown, and then it calls close, okay? And the issue here is that this cleanup routine is not guaranteed to close this socket, right? Because if the shutdown method throws a socket exception, then this is going to exit before close is called, right? This is kind of a classic type of bug that you see with resources. Really, the close call should probably be in a finally block or something like that. So now, if you think about kind of traditional type inference, right? I think most of the time, it's trying to infer behavior that's reflected in the code, right? That we try to infer annotations that we think actually match what the code does. And if we approached inference that way, we would not infer an owning annotation on this parameter, right? Because it's not guaranteed that this method is always going to close the socket. But in practice, that led to a bad outcome, right? Because potentially you have a bunch of callers who are already relying on this cleanup routine to actually close the socket. And sure, there's a bug here, but if I don't infer this owning annotation, then when I run the checker, you're going to get errors reported at all the client code that's relying on this cleanup method. It's going to say, hey, you're not closing this socket. And that's really not the best output of the tool, right? The bug is really right here that needs to be fixed. So what we do is we do this optimistic inference where we try to mirror the developer intent. It looks like you are trying to close the resource here. Usually when a method tries to close a resource, it intends to close it always, not just conditionally. So we go ahead and we infer this owning annotation on the parameter. And this will not be verified, right? You'll get an error inside this method when you try to run the checker. But arguably, that's where the bug fix is needed anyway, right? That if you fix the bug here, put the close in a finally block, then that's really, I think, what the developer intended to do, right? We can't do proofs about this, but it seemed to work better in practice. Yeah, we have a question?
So I'm wondering, is there any kind of exception analysis that you do for shutdown, or if this shutdown could never throw an exception, would you verify this property?
So in this case, I believe that this is a checked exception, that it's actually in the signature, that it throws a socket exception. Now, even if there were no exceptions declared, there are all kinds of exceptions that it might actually throw. A runtime exception, null pointer exception, all kinds of things. So we try to be pragmatic there. There's a set of like kind of standard runtime exceptions that we just ignore. And we're going to assume that methods are not going to throw them. Very often there are actually other checkers in the checker framework that you could use if you really want to get rid of those exceptions. Like you'd run the nullness checker if you want to get rid of null pointer exceptions. There's another one for array index out of bounds. But if you assume that any runtime exception might be thrown by any methods, the output of the tool becomes completely useless. So yeah, that's the story about exceptions for method calls. Other questions? Okay, so let me just show you an example of how our inference rules look for doing this inference. So here's a rule for inferring an owning annotation on parameter p of method m. So we check, okay, the type of method m's parameter is t. So with these rules, we just assume there was one parameter per method. So here that type is socket. And then we say, okay, for that type t, is there a method that must be called? So in this case, for sockets, we've modeled it as you have to call close on that parameter. And then here's where things become optimistic. We check, does there exist an invocation of that finalizer method, that resource releasing method within the body? We don't check, is it true that on every control flow path through this method is close called? We just check, did they try to call it? And if so, we go ahead and infer this owning annotation on the parameter. And I have a more detailed example, but that's in the bonus slides. So if we have time at the end, we'll get to that. But this is the basic idea of how the inference works. We've defined a bunch of rules. We handle owning fields, resource aliases, the must call annotation on types, and we run these rules to a fixed point. So let me show you some of the results. So first, we had a bunch of benchmarks that had been annotated by hand already. So a question is, how many of those annotations were recovered by our inference? I think the overall average across all these benchmarks was, between 75 and 80%. It's actually interesting how it breaks down. We looked at 3 proprietary C# services, and on those, we're actually able to infer 100% of the annotations that were written by hand. And then our numbers are kind of lower on these open source Java programs. And if I look at the causes, it's like sometimes there's a class that exposes multiple public methods that close a resource. And like the human being picked one based on reading the code that was the finalizer method, and our inference tool just picked the different one. It didn't know. There was another weird case where there was like an abstract class, and to understand which method was responsible for closing the resource, you had to look at the concrete subclasses, and we don't do that level of analysis. So I can't say there was like one quick fix to get this number up. There were just, sort of complex code patterns that our inference technique can't handle yet. But, overall, we were reasonably happy with these numbers. And then the next thing we wanted to look at was, what was the impact on the warnings emitted by the tool without running inference versus with running inference? So this is with no specifications. This column was without running inference, and this is with running inference. And you might think, oh, with the inferred annotations, I would expect the number of warnings to go down. But in many cases, it actually goes up, which is maybe kind of surprising. But then the reason is that we're actually discovering new wrapper types during inference, and that creates new obligations that must be satisfied, like new types that need to be closed. So here, if you go back to this MySQL connection, let's assume that we inferred all these annotations. Then after I do inference, the checker is now going to look at all the uses of this wrapper type and make sure that dispose is called on it. So it's actually interesting that, in certain cases, the number of warnings went up. We think that's due to finding a bunch of wrapper types that then need to have new things checked on them. And so finally, we kind of categorized the final set of warnings after inference. And first, we looked at the kind of the false positive rate. And it's, in the ballpark, at least for C#, of what we were getting without running inference, right? So this is pretty encouraging. The hope is that you're getting an almost equivalent false positive rate, but hopefully better warnings, because we've inferred a lot of the protocols that are being used to manage these resources. Very few warnings due to incorrect specifications. Like most of the specifications that we inferred were actually correct. There were cases where we missed specifications and that led to warnings. This is an area where I think we could improve. For C#, there's a lot of types that kind of implement the closable interface, but they don't actually manage resources. So there, manually, you can kind of specify, oh yeah, it implements closable, but this actually doesn't manage a resource. Our inference is unable to do that. So that led to false positives in C#. In Java, there are a lot of cases with owning fields that are mutable. And I didn't get into the details of this, but actually checking that those are managed correctly is more complicated than for a final field. And our inference doesn't do a great job yet with inferring all the necessary annotations to handle mutable fields that hold resources. In fact, that's one of the things that we're looking at in our ongoing work. So we're still pushing forward on this project. One thing we're looking at is resource leak repair. So actually, Akshay Ature and Jens Paulsberg published a really nice paper in the last FSE about automatically repairing resource leak issues, and they used our checker and were able to repair some of the issues coming out of it, but they didn't use the inference. So we're thinking that if we combine our checker and inference, and we're looking at some new fix patterns for these leaks, we might be able to do a better job of automatically repairing leaks in programs. So that's something we're actively pursuing. We generally want better handling of mutation, including arrays and collections. Remember I said this was one of the biggest causes of false positives. So this is hard. We're trying to take some inspiration from Rust and how it manages like arrays of resources and this kind of thing. But we've got to try to strike a balance here, right? We don't want to have you to annotate like every array manipulating code in your whole program. So this is still very much a work in progress. I don't think we have a good solution here. We're still thinking about it. We have other inference improvements that we're working on, and we're also thinking about applying this technique to other domains. So there's been a lot of work about structured concurrency and trying to not leak threads. We think that this tool could be helpful for detecting thread leaks. There's also been a lot of work on specification mining of the property that you always need to call this method on this type, and we want to look and see if we can integrate those mine specifications somehow with our tool and see if it works well for kind of verifying a bunch of extra properties that we didn't even define by combining with specification mining. So that's it. In conclusion, I talked about the resource leak checker. So with this insight that we can build the core verifier without doing whole program alias analysis, that we can do targeted alias tracking, we came up with a tool that I think is a genuinely kind of new trade-off in the design space. Like you need to write some annotations, but I think you can get much better confidence compared to other tools out there that you're really catching most of the potential leaks in your program. Then I talked about this resource leak inference technique. We use this optimistic inference to try to capture what we hope the developer intended rather than being super strict about it. And we had some pretty good results with that too in terms of finding manual annotations and getting a precision level that's similar to what you had without writing the annotations in the first place. So yeah, I'm happy to take more questions, and here are the links if you want to download either the Java or C# tools. So thank you very much.
Yeah, thanks for the talk, first of all. Just one question. I think you mentioned this, but I'm not quite sure. So there is a way to, for example, classes to contain multiple multiple sockets, for example, and without it being considered a resource aliasing, just normal containment, and this works. Okay, so there's really a different kind of special case for when it's an alias, but there's also the normal containment that's covered, and like.
Oh, right, so you're talking about a case where maybe I have 2 or 3 sockets that are managed by this wrapper class. So that's supported. Those can all be owning. It's just that it's no longer a resource alias with any of the individual sockets. So once you have that, our tool, well, you basically have to call the disposal method on the wrapper type now. I mean, I guess you can either do that or call it on all the sockets that you passed in, right? Because now you have multiple resources. So I think in that case, we can only verify it if you call close on the wrapper type. But we can still handle it. It's just not a resource alias anymore. So it's not a case where you can close this or that.
Very interesting. I wonder about the different results that you got for Java and C#. I wonder, is there anything fundamental the way these programming languages deal with resources that leads to the different results that you have? I think you had 2 positive cases on resource leaks, and there were apparently, I think, fewer in C# than there were in Java. I think it was this way around. Does this have something to do with the language, with the framework, or did you just miss more for one language?
It's a good question. To be completely honest, I don't think we have enough benchmarks really to make broad conclusions about like how programs are written in one language versus another. An issue that did crop up that definitely affects the checking algorithm is that C# does not have checked exceptions at all. So it becomes much harder to define a good heuristic for which exceptions to ignore and which method calls you should assume might throw an exception. Checked exceptions help a lot with that in Java. So that actually impacts like how the tool works. It's got the RLC# has more heuristics in it. And that might have an impact on these results too. It's kind of not exactly the same checking algorithm because of the lack of checked exceptions in C#. So yeah.
So to put it bluntly, you're not saying please use C# instead of Java if you want to avoid resource leaks.
I would agree with that, yeah. Or if you're designing the next programming language, like I know checked exceptions are kind of a pain, but if you care about resource management, it's really helpful to kind of know that this method you're calling might throw an exception, and it's declared there, and you should really, as a caller, think about handling that. From the perspective of resource leaks, that's really important.
All right, so let's thank the speaker again.